Okay, so good time to start. So we're very happy today to have Lorenzo Taggi giving a special probability seminar. Lorenzo Taggi from the Sapienza Università di Roma on macroscopic loops in the 3D spin-away double dimer and related model.
Okay, thanks for the nice invitation and for organizing this out of schedule seminar. So I'm going to talk about a system of interacting random loops, which are, I think, interesting mathematical objects on their own, but also are relevant since they are a description of other models. For example, the spin model, which is a relevant object, statistical mechanics, and also this class of models of random walk loop soups I'm going to introduce also includes the double dimer model, which is another relevant object. So the plan for my talk is the following. So I will start from the definition of the random walk loop soup in a quite general setting. Then I will discuss some special cases of this general random walk loop soup. We will talk about spin model, double dimer model, and monomer double dimer model. Also will talk about some connection to the problem of Bose-Einstein condensation. And yes, then I will state a general result about occurrence of macroscopic loops in dimension 3 and higher. And I will, in the end, introduce some ingredients of the proof. In particular, in the end, I will introduce a different random loop model, which is equivalent to the one which I will introduce at the beginning, and which has nicer features than the one I will start with. And so these are two equivalent formulations of the same random walk loop soup. Okay, let us start from the definition. So I refer to this model just as random walk loop soup. So the model is defined on a undirected finite graph. And we have to start from the definition of rooted oriented loop. So a rooted oriented loop is a sequence of vertices such that the next vertex is a neighbor of the previous vertex. The last vertex coincides with the first vertex, and we have at least two steps. So the rooted oriented loop then is a closed random walk trajectory with a starting point, which can be an arbitrary vertex of our graph. And we call LG the set of all rooted oriented loops in the graph G. And we denote by cardinality of L the length of the loop L, namely the number of steps which we have in the sequence. And so the configuration of the model, the configuration space of the model denoted by omega is so the elements of this configuration space are ordered sequence of rooted oriented loops. So an element omega, okay, we can see as a sequence L1, L2, Ln, where these are all rooted oriented loops, which can of course overlap, have some overlap. And later we are going to draw this configuration at random according to a certain probability measure. And cardinality of omega corresponds to the number of loops that we have in the configuration omega. And so an important variable that I need to introduce to define the probability measure is the local time, Nx. So Nx is the total number of times x is visited by some loop, so which corresponds to the total number of ingoing arrows I have at x, which also corresponds to the total number of outgoing arrows I have at x. And okay, now I'm going to define the probability measure. So the probability measure, so I will comment on all these terms which appear in the definition. And later we will see an equivalent definition, which is nicer from a certain point of view. So the definition depends on a weight function, which, and by choosing a different weight function, we obtain different models of interest. The weight function is just giving a weight to the local time. And for the moment is okay, an arbitrary function. And okay, let us discuss all the terms which appear in this definition. Okay, in the definition of the probability measure. So we have
now this weight function is on the vertices.
Yes, it is on the vertices. To comment on that. So in the definition, first you have one. Oops, not to raise. 1 divided by constant, which is a normalization constant, which makes this p the probability measure. Then we have 1 divided by the number of loops factorial. The number of loops factorial can be thought as a normalizations for the number of possibilities that I have to order the loops. So given a loop configuration, I have to decide which one is the first loop, which one is the second loop, which one is the third loop, and I have number of loop factorial possibilities for assigning this ordering or labeling to the loops, and 1 divided by number of loops factorial is normalizing that. So then I have product over all loops, and I have a factor beta to the length of the loop. So in this measure, the higher is beta, the longer are typically the loops. So increasing beta makes the total loop length greater. And I also have a normalization factor 1 divided by the length of the loop, which can be thought as normalizing for the number of possibilities that have to choose what is the starting element of the sequence. So if I take a loop with a starting point, and then I take the same loop with a different starting point, maybe the starting point here is going to now be here, I obtain a different loop. And this 1 divided by the length is normalizing somehow the number of possibilities that I have to choose for choosing the starting point. Okay, now we have an interaction. So the loops, according to this definition, interact locally through this weight function, which okay, is giving a weight to the local time. If the weight function was 1, so the function 1, then we will have no interaction between the loops. This would be a simpler model where this random walk trajectories are drawn independently from each other, so there will be no spatial interaction. But we will try to address general weight functions. And finally, we have a factor n½ to the number of loops, which is somehow relevant since we are going to make a connection to spin systems, and n will play the role of the dimension of the local spin space. Okay, so these are the terms.
Is omega a configuration of a sequence of loop omega 1 up to omega, or is it just a, in other words, does the 1 over w factorial take care of the ordering?
Yes, exactly.
The labeling?
Yes, exactly. So for example, if okay, let's think of this configuration that I draw here. Now, if for example, this black loop is called L1 and the red loop is called L2. If I now decide that this is going to be L2 and this is going to be L1, I obtain a distinct loop configuration. It's a different omega. And this omega factorial is a normalization for the number of possibilities that you have to decide what is the number 1 and what is the number 2. So it's normalizing somehow that. And okay, so I want to address
Lorenzo, and what if the same loop repeats multiple times in the sequence W? This does not affect the 1 over W factorial.
If the same loop,
can it be that L1 equals L2? It's exactly the same loop.
Yes, it can be that L1 equals.
But still you have the 1 over W factorial, although exchanging them somehow is the same.
Yes, exactly. And still, I always have, in the definition, I always have double factorial, although, yes, you're right. But essentially, this comment that I made is actually relevant for models where I cannot have the same loop 2 times. For example, the double dimer model. Right. Okay, so for that, there would be precisely, this problem will not arise. But as you said, yes, what I said is not precisely exact, since we might have the same loop multiple times.
And another question. I'm used to having n to the number of loops where n is the spin components, and now you have n over 2. So
Yes, because usually I think you're used to the case where the loops have no orientation.
Okay.
But this is the same because if I
yes, okay.
forget the orientation, then I have
Yes, right.
n to the number of loops.
Right.
Okay, so are there questions about this definition? Okay. So, so actually this configuration space, omega, okay, we have infinite configuration, so it's not, the measure is not well defined for any choice of beta, n, and u. So there is a condition which ensures that the model is well defined for any value of beta and any n. And the condition is that un is good, which means that somehow un is decaying quite fast, faster, or at least as fast as e to the minus n log n. If un was decaying as e to the minus n without log n, then the model will not be defined for any beta. There will be, for beta too large, we will have infinite weight function, infinite partition function. So this is a natural condition we need to impose. And okay, now I'm also going to introduce another quantity, which is the range of the weight function. Well, the range of the weight function is going to be somehow the maximal local time which we can observe in the model, depending on depends on the choice of the weight function. For example, if we consider this weight function that we can study, so we can say something about this model. So it is an indicator that the local time is less or equal than some constant m. This is going to be a weight function which has range m. And this is a model which is already interesting because we have some hardcore constraints in this system. And so the general question we want to address is about characterizing the size and the geometry of the loops in ZD. In particular, so my focus will be in dimension at least 3. Okay, so now I'm going to discuss some special cases of this random walk loop soup. Let us start from the spin-one model. Okay, the spin-one model, I recall briefly the definition. So the configuration space is a product of local spin spaces, which correspond to a unit sphere of dimension n-1. And we have a measure which, so in this integral, we integrate with respect to a product of Lebesgue measures. And we have a Boltzmann factor, which, if beta is positive, favors the mutual alignment between spins. And okay, this is a well-known object. N equal 1 is the easy model, n equal 2 is called XY, n equal to Heisenberg model. And so obviously it's related to the spin system. So this connection is used to describe, to prove useful properties of the spin system in the paper of Bridges, Froelich, and Spencer, where, so the connection is that if we make a specific choice of the weight function, okay, we have a constant at the numerator, and the denominator grows very rapidly with n, as fast as n factorial, since you have this gamma function, local n little n factorial. So if we make this choice of the weight function, then there is a connection to the spin system, which is that the spin-spin correlation can be expressed as a ratio of two partition functions, where at the numerator we have well, an object that I did not define rigorously, but so I call it zxy, which is essentially the weight function, which is essentially the partition function that of the random walk loop soup, which I defined before, but with a modification. And the modification is that I have not all loops are closed, but there is one loop which is open, and it is a walk which starts at x and ends at y. And at the denominator, I have that all loops are closed. And okay, and it is known from the work of Froelich, Simon, and Spencer that for arbitrary values of n, a phase transition takes place in the spin system. The phase transition is characterized by the fact that, okay, I'm considering dimension at least 3. If beta is large enough, then the claim is that correlations stay uniformly positive in the volume and also in the choice of the vertex x and y. And this is okay, it's a result which holds on the torus for general n, but in the special case n equal 1 or 2, there are some techniques which allow to prove the same result also on general graphs. And the question we want to address is whether a phase transition occurs also in the corresponding random walk-loop soup. And we want to, because, okay, of course, this ratio of partition function cannot be expressed as the probability of some event in the random walk-loop soup. So there is no direct way to deduce occurrence of macroscopic loops in the probability measure that I define from this result about uniformly positive correlation. And also we want to answer this question without using any spin representation and extending then this result to also to any weight function. Also, because by choosing different weight functions, we obtain other interesting models. So the other another model is the double dimer model. So the double dimer model, as I will explain, corresponds to this random walk-loop soup in the case where the weight function is the indicator that the local time is precisely 1 and n equal 2. So we had n half to the number of loops in the measure. Okay, then this means that n half equals 1. And so n equal 1 means that we really want one visit from loops at each vertex. And how is the double dimer model defined? So we draw uniformly at random 2 dimer configurations, namely subgraphs of the box such that each vertex has degree precisely 1. We draw them uniformly at random and independently. And when we draw them at random and we superimpose them, we obtain a configuration of random loops where you see that each loop which has length at least 4, like for example, this loop or this other loop, can appear with 2 different alternation of blue and red dimers. For example, this loop here can appear with the sequence red, blue, or blue, red. So each loop of length at least 4 has multiplicity 2. And so the models are equivalent since in the definition that I gave, as we observed, each loop gets a label. So there is and while here, the loops do not get a label. There is no ordering of loops. But the labelings in the measure that I defined before can be averaged out precisely because we have this factor 1 divided by the number of loops factorial. And in addition, also in the model that I defined before, each loop has a starting point, while here we do not have starting points, but the starting points can be averaged out because of this factor 1 divided by the length of the loop, which is in the probability measure. So, and also we get that loop of length at least 4 have multiplicity 2. In our case, the multiplicity comes from the orientation, while here multiplicity 2 comes by the different possibilities that I have to alternate blue and red dimer. And so the dimer model is well understood in 2 dimensions from the paper of Castellet, from the seminal works of Castellet and Temperley and Fisher. And so this technique, which is a 2-dimensional technique, allows to characterize the size and the geometry of the loops in 2 dimensions, and also some conjectures involving this scaling limit of the model. There are some conjectures which relate the scaling limit to the model to Schramm-Liouville evolution curves in 2 dimensions. And so we want to ask what happens in dimension 3 and higher. So what can we say about the law of the loops in higher dimensions? Okay, this is a model we can describe. Let us consider like another version of this, well, a generalization of the model, which is the double dimer model with monomers. Okay, so in this case, the weight function is the indicator that the local time is at most 1. And this corresponds to a double dimer model where I can also have vertices which have local time 0, so vertices which are namely monomers, which are not visited by some loop. And here, if beta goes to infinity, we recover the double dimer model, so we maximize the local time. And this model is not even well understood, not even in 2 dimensions, because the method of Castellane, Temperley, and Fisher does not work if we introduce a density of monomers.
Could you remind where the beta appears in your weights again?
Yes, so beta is, we have beta to the, okay, so we have beta to I from, here we are multiplying over all loops, and then we have beta to the length of the loop. Okay. Which means, okay, in this case, it's beta to the number of, to the number of to the length of the loops, total length of the loop.
Yeah.
Twice the number of dimers.
Yes, twice the number of dimers, yes. Well, when I say length of the loop, this means that this loop has length 2.
Yeah.
And so taking beta to infinity then has the effect of making the local time the maximum as possible at every vertex. And this model is related to the loop 1 model, which is also studied on planar graphs, specifically on the hexagonal lattice. So essentially, the model, the double dimer model with monomers corresponds to the loop 1 model when you suppress loops of this loops of length 2. And there are some results on about occurrence of macroscopic loops on the hexagonal lattice, but not in higher dimensions. Okay, so let us now, I will also introduce other generalization of this model, but let us now first state a result for a general result. So, okay, to state the result, I will define the loop visiting a certain vertex. So for any configuration omega, configuration of loops, let us define Ix as the label of the first loop visiting X. So I might have many loops visiting X. Ix is the label of the smallest label among all labels of loops visiting X. And gamma X is a random variable which corresponds to the first loop visiting X. So the loop which has the smallest, so here I should have Lix, I made a mistake. So Lix. Okay, so it is gamma X is the first loop visiting X. If there is no loop visiting X, gamma X is going to define an empty set. And the result that I'm going to state holds on the torus. So a torus of side length L. So it is a statement about occurrence of macroscopic loops in collaboration with Alexandra Whitman, who is my PhD student from Berlin. And so the statement is as follows. So we need to have n, which is at least 2. So, and it must be an integer. And I'm going to consider dimension at least 3. And this first version of the theorem that I'm going to state, and I will state another version, holds for any good weight function, U, which has large enough range. So because of this condition, this theorem does not cover the double dimer model, but there will be another theorem later. So any good weight function which must have large enough range, I will explain why it is a natural condition. Large enough means how large, the answer might depend on n and d. So if you fix n and d, then any weight function which allows sufficiently many visits at the vertices, there exists a beta finite such that if beta is larger than, so there exists a beta 0 such that if beta is larger, then uniformly in the size of the torus, two things happen. The first thing is that the length of the expected length of the first loop, well, the loop crossing a selected vertex, say the origin, grows with the volume. And the second claim is that for any xy, for any pair of vertices xy, which are at a macroscopic distance, namely at a distance which is proportional to the diameter of the box, we have that the probability that there exists a loop which visits precisely that two deterministically chosen vertices is uniformly positive. So, okay, so it is a claim statement about occurrence of macroscopic loops. And let us make some comments. Okay, so essentially, as I said, take two vertices with uniformly positive probability, there will be a loop visiting both. Okay, so first of all, I don't think this claim is true in 2 dimensions. For example, for some of the models that I discussed in that I mentioned, for example, for the loop and model in 2 dimensions, there is also a notion of occurrence of macroscopic loops, which is weaker than the one that I stated, weaker because we are in lower dimensions. For example, it is known that if I consider a box of radius of side length L, and then I inscribe a smaller box of radius L half, then for certain choice of the parameter beta, I will have with uniformly positive probability loop which surrounds the smaller box. But I don't think it's true that if we fix two vertices with uniformly positive probability, we are going to have a loop which is visiting precisely that two vertices. Okay, so for like to have what should be the general picture in high?
Is there a specific two-dimensional model for which it is known this Welsh in your framework?
Well, here I was thinking of the loop one model,
but that's not exactly in your framework.
Yes, exactly. That's actually my framework. No, I don't think it is known, but essentially, when I think, for example, of this. Well, I think it's true because I don't think that removing loops of length 2 changes the picture. Yeah, no, so it is just a conjecture, but yeah. Yes, it is not known. Okay. Probably it's possible to prove it for the double dimer model, since in 2 dimensions a lot is known, but I should check. Yeah, but I came to this claim by analogy with the loop one model. Yeah. Okay, so. Okay, to get the general picture, okay, so this result shows that we have macroscopic loops, but so the picture is that here we expect to have coexistence of microscopic and macroscopic loops. So it is true in this regime where we have macroscopic loops, we will still see a density of small loops. This also is possible to prove it. It's not so be hard, but I didn't write the proof. But then another claim, which is also true, is that the picture should be that there should is so contrary to percolation, where we have unique macroscopic clusters in the supercritical regime. Here we do not expect to have uniqueness. So here in the regime where we have at least one macroscopic loop, we expect to have with uniformly positive probability multiple macroscopic loops. And the idea, so how could one prove it? I don't know, so I don't have the proof, but the idea should be that the macroscopic loops do are space filling, and they somehow so the idea should be that with uniformly positive probability they exhibit that we have points of the trajectory where they get close to a point which was visited before by the trajectory. And if you can show that this is the typical behavior, then you can break the loop into two macroscopic loops with a finite cost, and then you can prove that you have multiple macroscopic loops. If you can show that somehow the picture that I draw at the beginning occurs with uniformly positive probability, then you can also show that you can break these macroscopic loops with a finite and positive cost into multiple macroscopic loops. And then you get that also with uniformly positive probability, you have multiple macroscopic loops. But I don't know how to make this picture rigorous. So this would be smart as a conjecture that you have multiple macroscopic loops. And also, there is also more precise conjecture. If you have questions, I can tell you later. So about there is a precise conjecture about what is the scaling limit of the distribution of the length of the loops. So the scaling limit should be somehow universal in three-dimensional and higher dimensional random walk loop soups.
But that Poisson Dirichlet distribution, will that depend upon the number of components? I mean, there's this weighted, Poisson Dirichlet.
Yes, so I think in this framework, the conjecture is that it only depends on the value of n.
N, yeah, but then
it does not depend on the weight function and does not depend on beta. So, well, I should somehow. So this conjecture involves only the macroscopic loops. So somehow I can explain later. So because of course the distribution in some sense will depend on beta and on u, but there is a way to formulate the conjecture such that the macroscopic loops, if you rescale the length by the total loop length, then you obtain an object which does not depend on the.
But there's a weighted Poisson Dirichlet distribution, right? It's not just the standard one, not just the uniform one. I forget what it's called.
Yes, I weighted depending on
depending on n. Now,
when n is 2, we should obtain the uniform Poisson distribution. Okay, so the methodology that essentially is that we are going. I'm going to define a different random walk loop soup, which is equivalent, which proves to be equivalent, but which is nicer to study because it has some nice features. For example, a notion of reflection positivity in the space of path, and we can prove essentially we reformulate the method based on reflection positivity of Froelich, Simon, and Spencer directly in the space of path without using any spin representation. And this allows to describe the properties of loops also in models which are not known to have a useful spin representation. For example, this double dimer model of this model with arbitrary weight function which does not correspond to a spin system. We do not know whether it corresponds to a spin system. Okay, so the proof also implies some new implications on the spin-1 model because so some of the proof implies that if the dimension is at least 3 and n is at least 2 and beta is large, then we get the information that this type of correlation is uniformly positive, and somehow this when you perform these expansions which allow to express the spin system as a random walk loop soup, you see that this correlation is related, but not precisely equal to the probability that you have a loop connecting x to y, but it's not precisely equal to that, but it is essentially in the proof we first, essentially if you apply if you consider our result for the weight function, which makes the connection to the spin-one model, then you obtain that this correlation is uniformly positive. So similar question to ours have been.
Does this make use of reflection positivity?
Yes, the proof. Yes, exactly. So essentially, it is a reformulation of the method of Freire, Simon, and Spencer, also from the point of view that you obtain information on different types of correlation, not spin-spin, not SX1, SY1, but it's a reformulation also from the point of view that you deal with different objects. So you study other correlations, and the way as I do is that, so I don't know how to obtain information on this correlation from the analysis of the spin system. The analysis really requires considering the random walk loop soup, and then in the end you reconvert the result into the language of spins. Maybe there is a way to do it directly for spins, but I don't know. Okay, so the theorem that I stated was also, it's actually this representation with some, well, actually the representation will come later, somehow is related to a model which was studied by Benassi and Ulci, so we also addressed the same question. And the result is holds for the spin-one model where n equal 2. Essentially, what they do is they use the result of Freire, Simon, and Spencer and reformulate this result in the language of loops. And this reformulation uses the reliable n equals 2 and the fact that you really have a spin system. So this is why the result holds only when for the spin-on2 model. And their notion of macroscopic loops is similar, but also has some differences. So they allow the loops to enter from the boundary and to come back to the boundary. But this result is based on the spin representation. And okay, another remark. Okay, it's not difficult to show that if beta is small, the probability of having a loop connecting x to y is exponentially small in the distance by using, for example, cluster expansion. Okay, so a comment is that the theorem, as I stated in the way it was stated, requires a large enough range of the weight function. This is a necessary condition if you want to state the result in Y generality for any value of n, because indeed our result complements a result from Chase and Coulters from year 2000. So essentially, what they do, they consider a loop model which is analogous to our random walk loop soup. So the constraint. So essentially, it's analogous to the case where the weight function has finite range, but in that case, this constraint involves the edges and not the local time at the vertex, but the local time at the edges. But it's somehow analogous.
So, what do you mean finite range?
Yes, finite range. So, a range of the weight function is the weight function is okay. So, a general function, and the range was defined as the what is the soup? Okay, this is the range. So it's the maximal local time which is allowed by the weight function. So if the weight function, for example, the range can be infinite, which is the case of the spin-one model. Namely, the weight function is positive for any n, or it can be finite. For example, this weight function has a finite range because you cannot, because this weight function does not make possible to have local time strictly greater than m. So this result involves, so the result of Chase involves involves any weight function which has finite range. And so the statement is that if you fix a weight function with finite range, then, so now the weight function is fixed, and you take n larger and larger, this is true in any dimension, even 2, then what happens is that if n is too large, you're not going to see the phase transition anymore. Maybe if n is sufficiently large, you're going to have for any beta, the exponential decay of the loop of the probability that x is connected to y. So this does not contradict our results, because instead our result indeed states that if you fix n and d, then you will find a weight function with large enough range such that you see the phase transition. So the idea is that if n is larger, then it will be necessary to consider a weight function with larger range in order to see the phase transition. And somehow,
who are the co-authors of Chase?
yes, so
Chase, Pliatko, and Stengel.
Yes, Stengel. Exactly.
Oh, so it's Lincoln Chase. Yeah.
Yes, year 2000. So it is yes. Well, they use also reflection positivity in the space of loops too. So it is a result about absence of phase transition. Well, somehow, yeah, okay, and this is okay. This is another interesting conjecture, which is the Polio conjecture, a very famous conjecture, which is for the spin one model, but it can be reformulated in the space of loops, and it is a very two-dimensional fact. So the fact that this exponential decay of correlation holds true for any beta in two dimension for any good weight function, as long as n is strictly greater than 2. So, so the Polio conjecture is usually referred to. Okay, actually, it involves the spin-one model, but then you can translate it into the language of loops, and this would be the conjecture. But somehow, so the fact that you have finite range makes the problem drastically different than in case of infinite range. Okay, so so the theorem that I stated before does not cover the double dimer model, and so this is the theorem about double dimer model, which the statement is that okay, the points 1 and 2 of the theorem 1 also hold in the specific case of the double dimer model, and essentially the strategy is similar to the one of the first theorem, but it's also a bit different in the sense that okay, it is what one does here is to use this technology to show that monomer correlations in the dimer model are uniformly positive, and then there is a way to deduce from this result of uniform positivity of the monomer correlation that we have macroscopic loops in the double dimer model. So it is a first one gets information on the monomer correlation in the dimer model, and then one makes the connection to the double dimer model. And this really requires the fact that you can decompose the double dimer model into two independent copies of the dimer model.
So just to understand how this relates to the theorem of Chase, Pliatko, and Stengel. So they showed that if you have a finite range, you can choose n large enough to have short loops. Here the range is 1.
So here is n equal 2.
Yes, n is 2, I understand. So somehow the way to understand it is that for n equal 2, things work out regardless of this factor. So you'd expect it to for other good weight functions as well, maybe for any good weight function when n equal 2. This is how to understand it?
Yes, because essentially this is the, okay, when n equal 2, essentially this is the minimal weight function I can get. It's the weight function which allows only one visit. So if I have weight function which allow more visits, then this can only get better.
But you don't have a theorem.
Yes, I don't have a theorem. I have a small theorem for the 2-point function, which is the ratio of partition function where I have a self-avoiding walk at the numerator, but not for this probability. I don't have the theorem for.
But the theorem you have for n equal 2 and the large class of weight function.
Yes, no, the theorem I have for any n. So
any n, but it doesn't contradict Chase.
No, so I have essentially that, okay, fix n and d, fix n and d first. Then there will be any good weight function with large enough range, large enough depending on n and d.
Right.
So if n is larger, this will force you to take an even larger weight function.
But the point is that because you have this theorem, and there is the theorem of Chase et al. As well, then it's a bit surprising that you can prove your result when n is 2 and the range is 1. But is it that we should understand that when n is 2, then the range doesn't matter, that it's always macroscopic loops, in your opinion?
Yes, in my opinion, yes. But the result of chase also requires n very large.
Yes,
it does not require
I
maybe
didn't say
n.
there is a contradiction, just to see what
Yes,
is
yes,
expected.
exactly. Yes, I would say so, because it's somehow the theorem that we have is for the weight function, which has minimal as possible local time. So if you allow 0, okay, you don't have macroscopic.
So specifically, like with range 1, maybe n equals 3 already wouldn't have.
Yeah, yeah.
Maybe.
Exactly. So actually, for example, we can, okay, it's easier to, so for the 2-point function, which is defined as this ratio partition function with an open walk and the denominator.
Yeah.
Okay, this is not the probability as here, but is a different. Also, there you can ask whether the 2-point function is whether the 2-point function is uniformly positive or not. And it seems okay to have a specific estimates, and it seems to me that if the weight function allows 0, 1 visits in 3 dimensions, it should work up to n equal to 7.
I see.
So there is something an explicit bound which involves comparing 2 constants, and then yes. But so getting information on this probability is a bit harder.
Okay.
Okay, maybe
Just to be on that theorem again, what is Poisson-Dirichlet statistics part of that theorem?
what? Sorry.
Poisson-Dirichlet statistics. Is that something you know?
No, as a conjecture. Poisson-Dirichlet has been proved in class of models where we have no interaction between the loops. For example, for the free Bose gas, namely, I don't have where there is no geometric interaction between the loops which are drawn at random. In that case, it is known, but I don't think it's known for any model where there is a real geometric interaction between the loops. Okay, so okay, maybe I could discuss some extension and then have 1 hour in total, right?
Yes.
So okay,
Roughly 12 more minutes.
yeah. So yeah, okay. So okay, we can. Actually, there is a nice, very important open problem, which is proving occurrence of macroscopic loops. For example, in the Bose gas, which is a model coming from quantum mechanics, and the question is proving Bose-Einstein condensation, which is somehow related to the occurrence of macroscopic loops in the corresponding random walk loop soup, which is somehow related but not precisely the same as the model that I defined, since we have these trajectories which are in the Bose gas, we have if we look at the model in discrete space, we have continuous time simple random walk trajectories, and if we look at the problem in continuous space, we have Brownian motion trajectories, closed random Brownian motion trajectories. And in both cases, we have loops, and there are many results from different small works by different people who try to prove the occurrence of macroscopic loops in this, but there is essentially no proof in a case where we have loops which have a geometric interaction, namely that the loops interact depending on their distance, and except for one case, which is the Bose gas where the interaction is local, so the loops interact when they touch each other, and for a very special choice of the parameter, which is the case of so-called half-filling condition. And so essentially wanted to push our technique forward and to see whether we are able to describe long-range interactions. So now I define then for this reason a generalization of the model where the probability measure is the same as before, but there are two differences. Okay, one difference is that beta is not called beta, but it's called lambda, because in this connection to the Bose gas, we should think of this parameter as a fugacity, and then I don't call it beta. But the other main difference is that we have a long range interaction. Namely, we don't have the weight function as before, but we have a long range interaction, which is in the sense that now the loops interact as follows. So the weight which is assigned by this potential is such that I sum over all pair of loops, Li and Lj, and given two pair of loops, Li and Lj, I sum over all pair of steps of these loops, and then I give a weight which depends on the distance between these two steps. So I like to say that if you look at the picture that I drew, then each step interacts with each other step depending on the distance. And if G is positive, we have repulsion. If G is negative, we have attractions. And we want to understand, okay, which type of interaction we can address. Turns out that there are choices of G that for which our theorem still holds. Okay, the case A is the case where the loops interact only when they touch themselves. Okay, this corresponds to the model that I defined before for a certain weight function. But so the case of longer interaction, okay, this is a trivial case. B, which is the case where there is a repulsion when the loops touch themselves, and an attraction when the loops are on nearest neighbors. The third case is a case where there is a repulsion when the loops touch themselves, and an attraction which decays exponentially with the distance. And the fourth case is the case where I have a repulsion when the loops touch themselves, and an attraction which decays polynomially with the distance. So the third theorem is that, okay, we also have macroscopic loops for as lambda is large enough and d is greater than 3. In the cases A, B, C, and D that I stated before. So there is also a way then to obtain results for loops which interact by long-range interactions. And okay, so this model somehow corresponds to the case where, as I said, each step interacts with each other step. So so this is an oversimplification of the Bose-Gas, but because here we have discrete time and also discrete not continuous time. But the point is that the main difference with the Bose-Gas, and this is something that we cannot describe, unfortunately, is that in the Bose-Gas, it is not the case that each step interacts with each other step, but somehow what you should think is that each loop is divided in two pieces, like some legs, and like each loop is divided in certain pieces. And then it is the case that, so it is not the case that each step interacts with each other step, but each step interacts only with the steps which of the other pieces, which occur in the same position of the other pieces. For example, the first step interacts only with the first, okay, let's say that I have a step starting from here. Okay, this will not interact with any other step, but only with certain steps. This one, this one, this one, this one. And so it sounds like a small difference, but unfortunately, the technique does not work in this case. And somehow this model that we can actually describe is a model where we have more interaction with respect to the Bose-Gas. And but so we cannot describe a model where we have less interaction. We can describe a model where we have more interaction. Okay, so now in the remaining few minutes, I will probably, okay, we'll just define an equivalent description of the random walk loop soup, which is okay, in 5 minutes, which is an equivalence description which has very nice properties. So in this description, the loops have no orientation, contrary to the definition that I gave. And also in the measure, as we are going to see, we don't have a factor n to the number of loops. But contrary to that, we are going to have that each loop gets a color. And the important thing is that we have to write the probability measure as the product of local variables, because if we have this description, then we can use a property which is important, which is the reflection positivity property. So, and to define the model, so the model will be defined into 3 steps. So we consider an undirected finite graph. And for example, we should think of a graph as this graph with edges which are not represented, which connect nearest neighbor vertices. And okay, to define the model, I define 3 objects. So the first object is the set of link cardinalities M. So an element in MG is essentially okay, an element in MG is a vector which is telling me how many times the edges are visited by some loop. So an element M is as represented in the picture, is such that ME is a natural number and is telling me how many times the edge E is visited by a loop. For example, on this edge, we have ME equals 3. On this edge, ME equals 1. On this edge, ME equals 1. This edge, ME equals 3. Here equals 1, 1, and so on. Here equals 2. Here equals 0, equals 0. And the condition is that the total number of times the vertex, so the total number of links which are incident to a vertex must be even. Okay, so now M is defined. For example, we can think of a M as the one which appears in the picture. Okay, now given M, I introduce a set of colorings, GMC, where a coloring is C is a collection of functions which assigns a color, namely an integer between 1 and n, to each link. For example, now we represent a pair M and C. You see that M is the same as before, while C is a coloring configuration. Each loop can be blue or red in this example. Okay, now M and C is fixed. I need to introduce the last object, which is a pairing function, pi x, and pi x is a pairing function which pairs links touching x precisely to another link touching x of the same color. So it is a specification of which link is paired to which other link, like in this picture. So this is the representation of a triplet M, C, and pi. And pi is telling me that, for example, this link is paired with this link, this is paired with this link, or this is paired with this link. This will be pi x, where x is this vertex, but I may also have other possibilities. I might have that maybe this is paired with this one, or this is this one.
But I can only pair with the same color, right?
Yes, but I can only pair with the same color. Exactly.
Lorenzo, pay attention to the time.
Yes, I think I just finished with the definition because okay, but I can say the details after the talk to those who are interested. Okay, so now this is specified. So MC, a configuration is a triplet, MC and pi. And now we can define a probability measure. And the probability measure is, okay, 1 divided by z. Then we have some factor that you can think as sampling the number of links according to a Poisson distribution, well, some factors. And then we have a weight function which weights the local time, and it's precisely the same weight function as before. As you see, we have no factor n half to the number of loops, but here loops have no orientation, and each loop has n possible colors. So this now makes the model equivalent to the previous model. And the important thing is that now a weight of realization is written as expressed as a product of local factors. Okay, this is equivalent to the previous model, only in case of no long range, in case where we have the first definition with no long range interactions. And there are two very important, nice properties of this representation, which are used in the proof. Okay, first of all, there is an equivalence. So the probability of having a loop connecting x to y in the first representation equals the probability of having a loop connecting x to y in the second representation. And so a first important property is that if I condition on the pair m and c, then the random variables pi x are independent. So under the probability measure, so if the random variable pi x, which tell you how the pairings are, it is the pairing configuration locally, these are independent random variables. And the second property is property of refraction positivity, which I will not be able to describe here. I went a bit slower than expected. But somehow these two properties are very useful, and one can see that they hold only in this alternative random loop representation, which has nice features, which has also been used to obtain recently new results about spin systems, where the spin model, for example, for large values of n, for example. And yes, I guess to those who are interested, I can say details of the proof after the talk. So if one wants to know more, because I don't have time to continue. Okay, thanks.
So in the double dimer model, on a torus, I guess you know that with positive probability of the far away points x and y are connected to each other, they're in the same loop, so you have a big loop.
Yeah.
You know that with probability close to 1, you have at least one macroscopic loop?
Okay, if it is probability going to 1, don't think. I guess maybe yes, in if the dimension increases, but I don't think that my
For 3, you don't know that.
For 3, I don't know. I don't think so. No.
Half the time you have a space filling loop, and half the time you have no big loops.
No, I only have a positive C. I didn't try to understand how large is this C. I guess my feeling is that things get better and better as the dimension is larger, but no, okay, I certainly don't have going with probability going to 1, but I don't even know. I think it's true that it's going to be probability 1.
Yeah, I mean, it seems absurd to think.
So
if there is a rotational symmetry in the spin space, then the spin-spin correlation is not equal to 1. If by spin you mean the sigma z consonant. So I wonder if it may actually dampen the initial expectation that it should go to 1.
Yeah, so
but I think Scott is saying that there is somewhere a macroscopic, not at specific location.
No, the question.
okay, you were saying not fixing the 2 points.
Not fixing the 2 points, just that
Okay. I didn't.
just the lower bound. It could be that half the time your largest loop anywhere is size 10. Half the time you have a single loop that fills up most of the space. So you rule out that.
I think that it's Poisson-Dirichlet. This conjecture means that we have the probability 1 at least 1.
Yeah, so
But I don't have this.
A little bit weaker than Poisson-Dirichlet conjecture.
Yes, I don't have this.
Poisson-Dirichlet is infinite, eventually the limit.
Yes. So yeah, so I don't have this information.
Michael?
Early on in the lecture, I don't remember which slide, if I heard correctly, you mentioned that there are results using reflection positivity on long range order. but also for other graphs. So are there some results of this type which do not use reflection positivity?
No, I don't think so. Well, actually, I can say that maybe there are some results. For example, now this technique of Tom for the spin O2 model. So it is a technique which shows that you have, which holds for the spin O2 that you have uniformly positive correlations, and this also on general graphs. And these can since you have, I think from uniformly positive correlations, when n equal 2, it should be possible to deduce that in the special case of the random walk loop soup, which corresponds to the spin O2 model, then you have macroscopic loops. Essentially, this is what Daniel Ucci and Costanza Benassi did, using the property of n equal 2. So, but he's somehow deducing the result from the uniformly positivity of correlations of the spin O2 model. And this is the only case that I know where yes, there is no reflection positivity, but my result also, our result with Alexandra also relies on the fact that we have a torus. So it's not, I thought of other graphs, but it somehow, so you have to use reflection positivity in all directions at the same time. So, so it's not with respect to reflections or possible reflections. And yes, so I didn't find any other graphs.
So all the models you described are all reflection positive, or what you had to put some conditions on them? I didn't quite.
No, the weight function. No, so all the models are reflection positive, and essentially the only thing which is necessary is for the model with no long range interaction, is to have to write the probability of a configuration with a product of local factors. So somehow this is local because somehow this function is only measurable. So it is a product of terms which are measurable at x. So there is nothing. So for example, if I had the factor n to the number of loops, this will not be local. Then the technique will not work. And this is why we want to introduce scholars, because then you can you have the same measure, but you don't have any more n to the number of loops, but you have somehow colors.
Yeah.
And this allows you to obtain this.
You still get the reflection positivity.
This description. So you have to and the proof essentially is that you take your configuration on the torus, you condition on the so it's okay. What is this line? This is a reflection plane. If you have a reflection plane, essentially this you identify two disjoint subsets of the torus, TL plus and TL minus. TL is the torus. And so what you do is that you condition on the loop configuration only on the boundary, and conditional on that boundary configuration, you will have that the law of the loop here is independent from the law of the loop here. And also you obtain some symmetry. And so you need to have this type of independence. So you want to write, you want that your measure satisfies this feature, namely that conditional on the boundary configuration, you can have that the law of the system into TL plus and in TL minus. So in TL plus independent from the law of the system in TL minus. So it's a sort of spatial Markov property.
Yeah.
Is it possible to make sense of 3½ colors?
Of 3½
Let's say you have n over 2, if n is 3, you have 3½ colors.
Yes, so I don't.
Yes. Not reflection positive anymore.
Yes, yeah, exactly. It will be good to extend. Well, okay. Yeah, exactly. So we need this integer n just because we have to use colors. But you're right. So the properties of these loops shouldn't depend too much on the fact that n is an integer. So the model is well defined for any n. So I don't know if it is. I don't know if it is reflection positive when I'm.
I think it's not.
Okay.
My guess is it's not. I mean,
Okay.
There is a result of Marek Biskup about something to do with reflection positivity for random cluster or something. However, the proof has a mistake in it, so
Yes, I was told there.
I'm not sure.
yeah, I mean, you can look at, for example, Q-state Potts models. If Q is not equal to, if Q is like 2.5 or something like that, not reflection positive anymore. I mean, this is what Slava Ryshkov tells me anyhow. I don't quite know how to.
There are these minimal models. So it's not so clear that any value of n or q, which is not an integer, is not reflection positive, because some of them do have some local representations, at least this LuPo-n model. Although, yeah, maybe solid and solid, for instance, some of them have local representations, though it's not clear that the local representations have reflection positivity, but in the continuum limit, this should lead to minimal models which apparently have reflection positivity. So maybe not only exactly integers, maybe there are a few others at least in what they mentioned.
Yes, okay, here the constraint that you need colors, but yeah.
Lorenzo, you mentioned that the random path model is used to obtain results on the spin-o-n model for large n. What is this?
That is, no, I mentioned that, no, I don't know if I mentioned that the spin
very end something. Okay,
no, I said that there is, no, okay, no, I said that here I meant that, I was referring so that this random path model, so this description is used to obtain results on the spin-o-n model in the presence of an external field when n is very large. It's what we were well, for arbitrary values of n, and the result is new when n is large.
I see.
Because when n is small, there is a Lienian theorem for exponential decay of transverse correlations. Yes, I meant that what we discussed before.
Yeah, so you can do that for any ON model with magnetic field.
Yes, so essentially it is a result that figures that but the result is it all involves transverse correlation.
Yeah.
So we have an external field which is parallel to the nth direction, and then we look at SX1. It is a joint work with Benjamin Lees. We look at this transverse correlation. And then, okay, essentially what you do turns out that you have to look at the model that I define, okay, here in the end, but the fact that you have an external field implies that you do not only have closed loops, which can have any color, you also have some loops which are open, which can only have color n because the external field points into the nth direction. And somehow it's still true that we have a factor beta to the total length of all paths, But in addition, the last step of the open walks, so of the open loops, get factor h. So actually we have h squared to the number of walks, because for the walks, the last step gets factor h and not factor b. And if you send h to 0, then these walls disappear. And yes, and then it is possible to prove, unfortunately, only for transverse correlations, that transverse correlation decay exponentially fast with the distance for any value of any positive value of h. And for truncated correlation, I was discussing with Ron before, does not work. One will need some equivalence of the switching lemma for transverse for the spin-o-n model with arbitrary values of n to obtain this result. And the proof uses somehow this framework that I was defining. So I was saying, okay, so sample any m and c, and now it remains to sample this local variable pi x, which are independent. So you can use a sampling procedure. For example, you want to know what is the law of this the loop starting from this link. Okay, then you sample the pairings at this vertex. And this can be paired to any other link of the same color, maybe this one. Okay, then you know that the walk is here. Then you can sample the pairing here. And so if you have an external field, essentially during this sampling procedure, at each step, your walk can die there. So it can, with a probability which depends on H, which is positive, H is positive. When you sample when you ask, okay, where is paired this walk? Okay, with positive probability, this might be, okay, somehow paired to a ghost vertex, or like you can think of it as dying. And then using this type of procedure, you get some exponential decay of transverse correlations. So this is why this pairing independence was very useful for this other work. But it's also used in our paper about macroscopic loops.
Okay, Lorenzo and also Wei will be here tomorrow as well. So they are staying at the IAS. So I suggest we postpone further questions to after the talk. Thank you very much.